Okay, so I guess we'll go ahead and get started for today. A couple of people have asked about the test. It's not quite ready yet, soon. Hopefully by early next week. I was just having a look at our schedule. We are more than halfway through the course, believe it or not. So today we're sitting at lecture 20. We will get 34 lectures altogether. We're 3 weeks out from the next test, so we still got a little bit of time there before we have to worry about it. November the 1st is the drop deadline. I'm committed to getting you the test back before the drop date. Not that I'm implying that anybody should drop. I think people are doing really well and working really hard. I'm really impressed with everything you're putting into the class. But a lot of people like to have a bulk of grades back before that deadline. So the test is going to be returned as soon as I can, but not today. Last day we focused about electric potential. That was a new definition. We found the expression for electric potential of a point charge, and we did some examples. We're going to do more of those today, and conservation of energy with electric potential. Before we get started, does anybody have any questions about anything? No? Okay, so we're good to get going. So in this example, we have a dust particle with a very small mass. There's our dust particle right here. And it has a small charge, 2 nanocoulombs. It starts from rest at point A. My T got cut off there. I'll just put that T back in. And moves in a straight line towards point B. What is its speed at point B? So it starts here, moves to here. It has an initial velocity of 0. We want the final velocity when it's over here. So I guess the V at A is 0. V at B is something we'd like to sort out. We know the mass and we know the charge. So we know M and we know Q0. So as we get started, we see that this is a charged particle. It's around other charged particles. We know it feels an electric force, and it's going to move because of the electric force. This has a positive charge, so it's repelled by this one. It's attracted to this one, so it moves away from the positive towards the negative. We know about that motion of charges. If you saw this problem cold on a test, you'd have to pick a strategy. You'd have to choose between kinematics and energy. This would be one of those problems where you should not use kinematics. As it moves from here to here, from A to B, the forces from these two charges depend on the distance. The distance changes, so the forces change, so the acceleration changes. Whenever acceleration changes, you can't use kinematics. Okay, so this would be an energy problem because you don't have to use acceleration. Okay, so this requires an energy solution. Let's write down our equation for conservation of energy. Energy at our final point is energy at our initial point plus the work done by non-conservative forces. We're going to say that our final point is at point B and our initial point is at point A. So it starts at A and goes to B. We don't have any friction or air resistance or anything like that that we're going to worry about. So we're going to say that the work done by non-conservative forces is 0. So our final mechanical energy is equal to our initial mechanical energy. So we'll say E at B is equal to E at A. Our mechanical energy is kinetic plus potential. So kinetic at B plus electric potential at B equals kinetic at A plus electric potential at A. Good to hear? So this is just our conservation of energy statement. Because we've introduced a relationship between our electric potential energy and our potential, we're going to use that in this problem. So, actually, I think I'm just going to move off to the side and do a little bit of work on the side here. So my kinetic energy at point B, here's my point B. My kinetic energy at point B is 1/2 times the mass of my particle times my speed at point B squared. Mass, I know, the velocity at point B, that's the thing I'm trying to find. My electric potential energy at point B, UE, all my pens are dying at the same time. I must have bought it all at the same time. Our electric potential energy at point B is the charge that's moving around, that's our Q0. So this is our charge that is sitting in the potential, so this is the one that has the potential energy, times the potential it is sitting in. Okay, so the charge that has the energy times the potential it sits in. This potential is the potential made by the two source charges, the plus and minus 3 nanocoulombs. So let's find that potential next. So potential at B is potential at B. I think just to keep our symbols straight, I'm going to label them Q1 and Q2. Okay. So my potential at point B is my potential at B from charge 1 plus my potential at B from charge 2. My potential at B from charge 1 is K times Q1 over R1. As soon as I write down R1 in my equation, I should identify R1 in my picture. So R1 is the distance between where I'm trying to find the potential and my charge 1. So this is my distance R1. Okay, so between charge 1 and point B. My potential at point B due to charge 2 is K times Q2 divided by R2. R2 is my distance between point B and charge 2, 1 centimeter. You good here? So that's K outside of Q1 over R1 plus Q2 over R2. K outside of 3 nanocoulombs divided by 0.02 meters plus negative 3 times 10 to the minus 9 coulombs divided by 0.01 meters gives us a potential of minus 1,349 volts. So sorry I went off the slide. Tragedy of zooming in. Okay, so that's my potential at point B. If I put that and multiply by my charge, then I can find my electric potential energy at point B. So UE at point B is my charge QO times the potential it's sitting in. QO is 2 nanocoulombs. Multiply that by the potential of minus 1,349 volts. And we get a potential energy of our dust particle when it's at point B equal to minus 2.697 times 10 to the minus 6 joules. Okay, so there's my electric potential energy at point B. You good there? If you didn't find the potential, if instead you did, when the charge was here, K Q1 Q2 over R2 plus K Q1 Q2 over R2, that would work too. You'd get the same answer. Okay, so 2 different ways to get at the same answer. So there's my kinetic and my potential at point B. Let's find the same thing at point A, kinetic and potential at point A. So point A is when my charge is up here. My kinetic energy at point A is 1/2 times mass A times VA squared. That's just 0. So it starts at rest. It's released from rest. My electric potential energy at point A is my charge of my dust particle times the potential it's sitting in. So the charge is easy, 2 nanocoulombs. Now I need to find the potential at point A. The potential at point A is the potential at A due to charge 1 plus the potential at A due to charge 2. Potential at A due to charge 1 is K times Q1 divided by R1. R1 will be the distance between our charge 1 and A, 1 centimeter. Plus K times Q2 over R2. R2 is between A and charge 2, that's 2 centimeters. So we've got K outside of 3 times 10 to the minus 9 coulombs divided by 0.01 meters plus minus 3 times 10 to the minus 9 coulombs divided by 0.02 meters gives us a total electric potential of positive 1349 volts. So that's the total electric potential at point A. To get the total electric potential energy, we multiply that by the charge. UEA, 2O times VA, 2 times 10 to the minus 9 coulombs times plus 1349 volts gives us a total electric potential energy at point A of plus 2.697 times 10 to the minus 6 joules. Okay, are we good to there? So I found the kinetic and potential energies or expressions for them at points A and B, and I know I have conservation of energy between those 2 points. So now all my K's and U's, I'm going to fill into my equation over here. So KB is 1/2 times the mass times VB squared plus UB. UB is negative 2.697 times 10 to the minus 6 joules equals K, that's 0. Plus 1/2 times M times 0 squared, that's our K, plus U, which is positive 2.697 times 10 to the minus 6 joules. If I want to solve for my VB, I'll take my 2.697 to the other side. I have to multiply that by 2, divide everything by the mass, 5 times 10 to the minus 9 kilograms, and then take the square root to get our V. What we get is 46.4 meters per second. Okay, any questions there? So if you know the potential, then you can figure out how to use your conservation of energy. Okay, so for our next example, let's stick with things that are in a line. So we're going to flash back to chapter 21 for a second. So, way back in chapter 21, we had 2 charges on the x-axis. Q1 was at the origin, and Q2 was at 5 millimeters. We said that we could place a third charge at x equals, so our charge Q1 was at the origin right here. We said that we could place a third charge over here at minus 12.1 millimeters. And if we placed our third charge here, the net force on it would equal 0. Okay, so that was an example we did back in chapter 1. When we solved that problem, we thought about electric forces. We said if Q3 is positive, then the force on this one would be to the left. The force from this one would be to the left. The force from this one would be to the right. Because this charge is smaller and this one is bigger, putting our charge out here would make those forces balance. So we found the net force to be 0 by recognizing that they had to be equal and opposite. And the equal bit was important because they were vectors, right? And the opposite because they were vectors. So we're going to take this to the next step. Our first question here, where on the x-axis is the electric field equal to 0? Well, if the force is 0, the field has to be 0 because force is charge times field. So out here, our E1 would point to the left, our E2 would point to the right. The net force is 0, and the net force is the charge times the electric field. So E is F over Q is also 0. So if the net force is 0 there, then the net electric field is 0 there, because at this point they're equal and opposite, and we had to draw those vectors. So that's a very quick recap of an example we did in chapter 21. So our answer here is also 12.1 millimeters. Now we're going to ask a new question. Where is the electric potential 0? And this one, you might be first tempted to say minus 12.1, okay, because the field is 0 there. That would be tempting. So let's just put a pause on that. Let's try and figure it out, and let's see if that's true, okay? Because electric field and electric potential are not the same thing. Electric field is kq over r squared, and it's a vector. Potential is kq over r, and it's a scalar. So potential and field are not the same. They don't necessarily have to be 0 at the same place. Okay, so they don't have to be the same, even though you might guess that they are. So V is different because V is a scalar. So V is a scalar. To get our net potential to be 0, so our net electric potential is going to be V1 plus V2 equals 0. To get those to sum to 0, it means they have to have opposite signs. And that bit's okay. That bit is going to happen. This potential will be positive because we have kq over r where q is positive. This potential will be negative because it's kq over r where q is negative. So they have opposite signs and equal magnitudes. To get equal magnitudes, the distance is going to be important. To get equal magnitudes, you want to be a little bit closer to the small charge compared to the big charge, right? So your big charge has to get balanced with your small charge. So there are two possible places where you could be closer to the small charge than to the big one. So you've got two choices. If I draw a dot right here, so this is choice 1, I'll label that A. Right here I'm closer to the small one than I am to the big one. Right? So that feels like a possibility. Another place where I could be closer to the small charge is out here. We'll call that one point B. Okay, makes sense? So at both A and B, they'll have opposite signs for the potential. And I feel like maybe I've fulfilled my requirement for the distance, that I have to be a little closer to the smaller one. So let's go through the process and let's see what we get for our answer. And you might notice at A and B, we are not drawing vectors because these are not vectors. Okay, we can't draw potentials because they're not vectors. So let's go through each of them. So we'll go through A first. So at A. So V1 plus V2 equals 0, because that's the condition we have, whereas the total electric potential equals 0. So K times Q1 over R1 at point A plus K times Q2 over R2 at point A equals 0. I put these in my equation, so I need to put these in my diagram. R1A is the distance between charge 1 and point A. R2A is my distance between charge 2 and point A. Charge 1, charge 2. If I look at my picture, I can see that R1A plus R2A equals 5 millimeters. So this plus this is 5. So R2A equals 5 millimeters minus R1A. So that's a relationship I just see from looking at the diagram. I'm going to fill in all the things I know from my picture. But I think first I'm just going to divide through by my K's. So divide both sides by K. Q1 is plus Q over R1A plus Q2 is negative 2Q over 5 millimeters minus R1A equals 0. Now I'm going to divide both sides by Q. Gonna bring this to the other side. So 1 over R1A equals minus 2 over 5 millimeters minus R1A. This is something I can solve. I'm gonna cross multiply 5 millimeters minus R1A equals minus 2 times R1A gives me R1A is 5 millimeters over 3.
What does say minus 2?
Oh, wait, plus, there we go. I was just catching that myself at the same time. R1A is 1.67 millimeters. So the electric potential is equal to 0 at X equals plus 1.67 millimeters. Okay, so that's one spot. Now we also have to think about the other spot at B. Same condition, V1 plus V2 equals 0. K times Q1 over R1B plus K times Q2 over R2B equals 0. R1B is the distance between charge 1 and point B, R1B. R2B is between charge 2 and point B, R2B is 5 millimeters plus R1B. So again, we have a relationship between those two distances. This plus this gives us the total distance, R2. I'll divide both sides by K. Fill in the stuff that I know. Q1 is plus Q minus 2Q divided by 5 millimeters plus R1B equals 0. Get that to the other side. Divide both sides by Q. Do our cross multiplying. 5 millimeters plus R1B equals twice R1B. So R1B equals 5 millimeters. The last thing we have to be careful of here, we see that R1B, the distance between 1 and B, B is to the left of the origin, so that would be a negative X value. So there's a difference between the electric potential and the electric field. The electric field could only be 0 in one spot because we had to account for the vector signs, for our vectors pointing in different directions. The same thing is not true for the electric potential because they don't point in any direction. They're either positive or negative. Okay, questions? Okay, so that takes us through our examples of finding the point charges. So next we're going to get to work on an equation. So during our last class, I had put up this slide, and I said we knew the relationship between force and field. We knew the relationship between force and potential energy, and we knew the relationship between potential energy and potential, but we didn't yet have the relationship between electric field and electric potential. That's where we're going to next, is we're going to develop that relationship between electric field and electric potential. And this is sort of interesting because we're going from a vector to a scalar. How do you go back and forth between vectors and scalars? So that's what we're going to do on this next slide, and that's going to take us a fair chunk of time here to go through this one. So we're going to start by asking what's the relationship between potential and work. So we know that our electric potential is electric potential energy divided by charge. And we know that the change in electric potential energy is the negative of the work done by the internal forces or the work done by the electric field. So those are the strategies we're going to use to figure out this problem. So we'll start by writing down this expression. So our change in electric potential energy is the negative of the work done by the electric field, because that's the definition of the potential energy or the work done of a conservative force. That's how that works. Our expression for work done is the integral of the force over the path. So when you exert a force along a path, that does work, and it changes the kinetic energy and it changes the potential energy. So S is the path taken by the moving object. Okay, good to hear. And in this case, this would be the path taken by the moving charge. So now let's put in the next relationships that we know. Let's relate electric potential energy and electric potential. So delta U is Q times delta V, because we said that potential is energy per unit charge. And we know that electric force F is charge Q times electric field. Okay, so those are our definitions of energy and force. We'll substitute those two expressions in. So Q times delta V equals negative Q times electric field integrated over the path taken. Okay, so I did a straight substitution there. You might recognize in both of these sides of the equation I have a Q, so I can divide both sides by Q. It's just a scalar. So then that gives me a result it's probably important enough to write in a big pen. That our change in electric potential is the negative of the integral of the electric field over some path. So this is kind of a big result. And what this tells us, and we're going to go into depth about what it exactly tells us, but it tells us that the change in the potential is related to the electric field in space. Okay, so that's the relationship. Here's our field, ds is our space, and delta V is our potential. So delta V tells us about what the electric field looks like in space, and that's some stuff we're going to cover for a little while. Okay, any questions to hear? Yep.
If you are given the electric field and we need to find the voltage, should we do negative differentiation?
We're going to come to that, but the short answer is yes. Yeah. Okay, so let's start looking at this equation and seeing what all the different bits of the equation tells us, because it's all really pretty important physics. So the first bit would be a simplification. If you had a case where your electric field was constant, then the integral of E dot delta S would just simplify to E times delta S. Okay, so an integral of E over the path would just be E times the change in the path. So point one, if E is constant, then delta V is equal to negative of the electric field dot delta S, where delta S would be a displacement. Okay? And then you would do that dot product the usual way. That would be the negative of the magnitude of the electric field times the magnitude of the displacement times the cosine of the angle between them. That's one way to find a dot product or a scalar product. The other way would be if you knew your components. So that would be minus EX delta X plus EY delta Y plus EZ delta Z. Okay, so if your electric field is constant, this is how you can find your change in potential, depending on which form of the scalar product you're able to use. Okay, so that's for a constant field. Good at that level. Okay, point 2, points 2 and 3 probably are going to deal with the fact that we're a scalar product here, this dot product. So what if the electric field is perpendicular to the path? If E perpendicular to delta S. I'm just using some shorthand in my writing. You know, technically I should be writing out the words if the electric field is perpendicular to the path taken, but those are a lot of words to write down, I don't want to. That would give us that our change in potential is minus E times delta S. Perpendicular means the angle between them would be 90 degrees. And the cosine of 90 would be 0. Okay, this is a good result. It's sort of interesting. Notice that this says delta V is equal to 0. Delta V equals 0 along any path perpendicular to the electric field. If delta V is 0, be careful, that doesn't mean your potential is 0. It means the change in potential is 0, so the potential itself is constant. So if delta V is 0 along any path, V is constant on any path perpendicular to E. And if you want to read ahead in the book, this is the part that's going to take us to our equipotential lines and our equipotential maps. So that's where we're going to go with this concept. So that's what happens if we move on a path perpendicular to the electric field. You might ask what happens if we move on a path parallel to the electric field. So that'll be our point 3. If E is parallel to delta S, then delta V is minus E times delta S times cosine 0, which is not going to be 0. So delta V is non-zero, means V changes along any path parallel to E. So if you move perpendicular to the electric field lines, no change in potential. Parallel to the field lines, there is a change in potential. Okay, so that tells us all about that dot there. That's the interpretation. Next, we want to think about the negative sign. What does that tell us? Because that negative sign means a lot. So what the negative sign tells us is that electric field has to point towards lower potential. So electric field points toward lower potential. That comes from the negative sign. If we want to see how that works, let's imagine we have an electric field that points from point A to point B. So here's our electric field vector. There's point A, there's point B. And let's say we go along some path from A to B, delta S. So there's our path. It's parallel to the electric field, so there is going to be a change in potential. Stuff is happening there. Our change in potential, delta V, is our final potential B. Subtract our initial potential A, so VB minus VA. That's equal to, use our equation, negative E times delta S times cosine of 0 equals minus E times delta S. So that tells us that delta V is negative. Which means that VB is less than VA. So if you move along that path, we're going towards lower potential. So often in diagrams, particularly in capacitor problems, but lots of other ones as well, we'll go ahead and we'll say that electric potential points from high potential to low potential. So we're going to do that in a lot of our diagrams, label them high to low potential. So electric fields will always point towards lower potential. Still good? Okay, one last comment about this equation, and that's to go to your question. So how do we find electric field if we know the electric potential? And the reason why that's convenient is because you can drop into Princess Auto and you can buy a voltmeter, and you can get them as cheap as $5. You cannot drop into Princess Auto and buy an electric field meter for $5. You can spend $1,000 to get an electric field meter. So if you can measure the potential, it's easy to figure out the field. That's why it's good to be able to know that relationship, is what you did in your last lab. So 0.5, since our change in potential is negative the integral of E dot ds. So to find potential, we have to do the integral of electric field. The flip side, to find the electric field, we have to do the derivative of potential. Here's where we have to be careful about the scalar and vector business. To flip it around, what we have is that some component of the electric field is the derivative of the potential with respect to that direction. Okay? So, for example, in Cartesian coordinates, and these are the ones we'll use most often, Cartesian, x, y, z, the x component of electric field is the derivative of the potential with respect to x. I am writing down the partial derivatives here. This is just like what we did in our wave stuff. You know, we took the partial derivative with respect to time, we held time constant, and we took everything else as, we took time as the variable and everything else is constant. Likewise here, and we will get around to some examples. The y component of the electric field would be the change in potential in the y direction, and the z component would be the change in potential in the z direction. You might think it a little bit funny, but most often, most students do these derivatives exactly right, and the reason they don't get full marks on the problem is they leave out the negative sign. Okay, so note to self, don't drop that negative sign. And then when you're writing your vector, you would say your vector E is the x component in the x direction plus the y component in the y direction plus the z component in the z direction. And that would be the second reason why people would lose marks. They don't write their answer as a vector. So just kind of careful with your notation and stuff there. We also know that when we have point charges, the electric field is radially outwards. So sometimes we want that radial direction. So with a radial component, the radial component of the electric field would be the change in potential in the radial direction. Okay, so those are the two ones we're going to see. This is when you have potential as a function. If you just had a couple of discrete points, the field is still the change in potential over the change in space. But if you had discrete points, you would say Ex is minus delta V over delta X. Ey is minus delta V over delta Y. And Ez is minus delta V over delta Z. Okay, so this is for if you had V as a function. This is for if you had V as a couple of points. Okay, that was a huge amount of information in like 10 minutes. Any questions? Okay, so I'll get everybody caught up with the notes, and then we'll come back to that slide and we'll write down all of our relationships. And we're going to do examples of all of this stuff. So we'll look at all of it. We won't have to just jump straight from theory into problems. Yeah.
Are points 2 and 3 assuming that E is constant?
It's also true if E is not constant because it's there in the integral as well. So if the path was perpendicular to the electric field, right, even if it's not constant, we'll still get a 0 here, likewise with a parallel. Okay, so to come back to our equations slide, our relationship between force and field, we know that F is equal to Q times E. And on the flip side, E is Q over F. Oh, sorry, F over Q. Okay, so that's our relationship between force and field. Our relationship between force and potential energy is that some component of force is the change in potential energy with respect to space, or delta U is the integral of force over space. Okay, so there's our relationship between force and potential energy. Between potential energy and potential, we know that U is equal to Q times V, and V is U over Q. Okay, so those were ones we had all covered before today. And now today we get into this one. I want to write this one sideways. So what we found from here is that delta V is the integral of E dot ds, or in discrete terms, delta V is minus E dot delta S. And our components of electric field are the derivative of potential in that direction, or in terms of discrete points, delta V over delta S. Okay, so there's our relationship between all of our quantities. I think this will be a good reference slide for you when you're going back and forth trying to figure all this stuff out. The ones that are typed, this is all about point charges. The ones that are not typed, the ones that are handwritten, those are for the relationships in general. Okay, so point charge or any other sort of field. Any questions? No, okay. So we still have a little bit of time. Let's look at the potential in a capacitor, because we do a lot of stuff with capacitors. So what is the electric potential? And it might sound a little better if we said the electric potential difference between the plates of a capacitor. So let's think about what we have for our capacitor. Our picture shows the electric field. I'm going to put on a coordinate system of x and y, because my electric field is a vector and I'd like to be able to put it in with a vector notation. So my electric field is minus the magnitude of the field in the x direction. So everything is in the horizontal there. I know that to find my change in potential, or my potential difference, I would do delta V is negative E dot delta S. Delta S is going to be some path between the plates of the capacitor. I'm going to choose my path to start here and just go all the way over to the other side. So there's my delta S. I see that my delta S I picked to be entirely horizontal, so delta X in the X direction. Okay, so there's my field, there's my path. If I put this in my equation here, I've got minus E times delta S times the cosine of the angle between them. My electric field is to the left, my path is to the right, my angle is 180 degrees, and cosine of 180 is negative 1. Gives me E times delta X. Okay, so the magnitude of my path is delta X, magnitude of my field is E, minus times minus 1 gives me positive. So delta X is the distance I go from one side of the plate to the other. Way back when we started all this stuff, we took our negative plate as our origin. We can call that X equals 0. And then the width of the capacitor, we often call that D. Okay, so our final position, the position of the positive plate, would be D. So that's E times D minus 0. So the potential difference between two plates of a capacitor is the size of the field times the size of the plate separation. As we go through problems, particularly conservation of energy problems, it will be very important to know which plate is at high potential and which is at low potential. So let's remember that electric fields point from high potential to low potential. And pretty much every problem we do from now on where we put in an electric field, we'll be labeling areas of high potential and low potential, just so we keep all those things straight. Okay, questions here? All right, so that's between our capacitor plates. Our last question, and we started this when we talked about electric potential energy, and we talked about the electric potential energy of charges in constant electric fields. And what we said was that charges always move towards areas of low potential energy, and that's true. That's how the universe works. Let's add context of what do charges do with regards to potential. So what would happen if I had a positive charge in between the plates of my capacitor and I just let it go in the middle? Well, if I think about what happens with regards to force, it'll be repelled by this plate and attracted to this plate. It will move to the left. Okay, so if I release a positive charge, it will move in the same direction as the electric field. It will move towards lower potential because we see it's going towards the low potential plate. And also to lower electric potential energy. Okay, so our electric potential energy was charge times E times position. That's a high potential energy. That's a low potential energy for that positive charge. Okay, what would happen to a negative charge released in between those plates? So if I had a negative here, it would move this way. It would be attracted to the positive and repelled by the negative. So minus Q will move against the electric field. Because that would be the direction of the electric force. The force is charge times field. The force would be a negative charge times the field, so in the opposite direction. We see that our negative charge moves towards high potential. And because our charge is negative, that's still lower potential energy. So our behavior is still the same. So we've been talking about points 1 and 3 all along. Now we just add in point 2. So a positive charge will move towards lower potential, a negative charge would move towards higher potential because those things correspond to lower potential energy. The last thing we could do on this slide if we wanted to, we could make a plot of the electric potential as a function of distance, and we would see that that would be linear. Because the electric potential would be E times the position X. So if we did the graph, that's what it would look like. Okay, the next thing we have to do is a capacitor example, but we definitely don't have time, so let's not even start it today. So we'll start with the example when we're back on Monday.